We are studying characterization techniques, how inorganic material can be characterized by different techniques. We have previously studied XRD, electron microscopy, and neutron diffraction for characterization of solid. And here is new technique which is also related to X-rays, but it is not X-ray diffraction, it is X-ray absorption spectroscopy. In X-ray absorption spectroscopy there are two techniques, extended X-ray absorption fine structure and X-ray absorption near edge structure. So first we will study about first technique, that is extended X-ray absorption fine structure. So first we will study about EXAFS. What is EXAFS? Extended X-ray absorption fine structure. In high energy accelerators, electrons are injected into an electron storage ring. This is electron storage ring which is present in high energy accelerators. Electrons move around this circular path due to series of magnets. There are different types of magnets which are placed here, and due to the magnetic effect, because when the electrons travel under the effect of magnetic field, they follow a curved path. So due to these magnetic fields, the electron will move in a circular path, and the diameter of this ring is 30 meter, and electrons are accelerated around this circular path by series of magnets. When the electrons are accelerated to kinetic energies above mega electron volt range, when this kinetic energy is reached, when the electrons gain sufficient speed and their energy is in mega electron volt range, they are traveling close to the speed of light. Their speed is very close to speed of light, that is 3 into 10 to the power 8 meter per second, and they emit so-called synchrotron radiation. When the electron, what is synchrotron radiation? Synchrotron radiation is the name given to the radiation which occur when charged particles are accelerated in a curved path or orbit, like this curved path, and the classically any charged particle which move in a curved path or is accelerated in a straight line path will emit electromagnetic radiation, and this type of electromagnetic radiation is called synchrotron radiation. So the electrons moving in circular path, they will emit the photons, and this type of or radiation, and this type of radiation are called synchrotron radiations. Okay, in EXAFS experiment, the X radiation is absorbed by a bound electron in a core shell. The electron which are moving in a circular path, that electron come from K shell. When X-rays fall on the atoms K shell electron are ejected, and that K shell electron will move in circular path, and they will emit photoelectrons, and they are called photoelectrons. Photoelectrons are those electrons which can emit photon. When they are de-excited, they will emit photon. If you measure the absorption coefficient of the sample as a function of X-ray frequency, a sharp rise or absorption edge is observed at K-shell threshold energy. So when this type of graph is drawn, these are different graph, and the y-axis is absorbance. We can draw on y-axis absorbance coefficient, on x-axis is energy. On x-axis there can be a frequency of X-rays, there can be energy of X-rays. There are different types of graphs. Okay, this is pre-edge, and here the edge is formed. This peak is called edge. So when absorbance and energy graph is drawn, or we measure the absorption coefficient of sample as a function of X-ray frequency, a sharp rise or absorption edge, this sharp rise is called absorption edge, and this absorption edge is formed it K shell threshold energy. This energy which here is rotated, this energy is K shell threshold energy, mean that amount of energy for which the electron will be emitted from the K shell. That amount of energy, that minimum amount of energy is called threshold energy, which is required for emission of electron from K shell. Each element has its own characteristic K shell energy because the element's properties are different from each other. So this peak for each element is formed at different energy levels. Okay. Each element has its own characteristic K shell energy, and this makes it possible to study one type of atom in the presence of many others. Because we can study mixture of atoms, because each atom will form the absorption peak or this absorption edge at different energy. So in the presence of other atoms, one atom can be identified by tuning the X-ray energy to its absorption edge. When the X-ray energy will be equal to the absorption edge, this absorption edge will be formed. The appropriate frequency X radiation from the continuous synchrotron radiation is selected by using Bragg's reflection from single plane of carefully cut crystals such as silicon or 220 plane. Often two crystals are used as illustrated in the schematic diagram of double crystal monochromator in figure 2.22. So here is broad spectrum X-rays which fall on silicon 220 plane. Then after a reflection from this 220 plane, they fall on another silicon crystal whose 220 plane is in front. They fall at a Bragg angle and monochromatic X-rays are produced. Bragg reflection from double crystal monochromator. This is double crystal monochromator which convert the broad spectrum X-ray radiation into monochromatic X-ray radiation. So this is monochromator made up of silicon crystal from the Bragg's equation, and lambda is equal to 2d sin theta. We have already studied this equation. D for the planes of the crystal stays constant, so changing the angle changes the wavelength of X-ray reflection. By changing this angle, this wavelength can be changed according to Bragg's equation. Okay, by changing carefully cut crystal mean the crystal cut in such a way that its 220 plane is in front of X-ray radiation. By changing the Bragg angle of reflection, the frequency of the X-rays selected may be changed. By changing just this angle according to this equation, if this angle is changed, then the wavelength will be changed and hence frequency will be changed, because there is direct relationship between wavelength and this angle theta. So just Bragg angle changes, X-ray frequency or X-ray wavelength can be changed, and we can select the desired X-ray wavelength or X-ray frequency by changing the Bragg's angle, and thus the absorption edges of the wide range of element can be studied. So each element require different frequency of X-rays, different wavelength of X-rays for ejection of K shell electron and for making of absorption edge. So we can produce different wavelength of X-rays, different frequency of X-rays by this type of monochromator, which is double crystal monochromator made up of silicon, and we can produce different wavelength X-rays, and the different wavelength X-rays have different energies and they can be used for different elements for ejection of their K shell electron, because a threshold energy is required for ejection of K shell electron, and when K shell electron is ejected in the graph, absorption edge is formed. So different X-ray frequency will form absorption edge of wide range of elements. And this is the diagram. Again, the diagram. This is the peak for different elements. For example, potassium give peak or absorption edge on different energy level, calcium on different energy level, silicon in different energy level. So different elements can be identified in X-ray absorption spectroscopy because each element has different absorption edge on different energy, because the threshold energy of the K shell is different for different elements. We have studied about this. This is about rhodium absorption edge, which is formed on this energy. Synchrotron radiation. We have studied synchrotron radiation, the radiation which are emitted by the electron that are moving in circular path. That type of radiation are called synchrotron radiation. So this is the graph related to synchrotron radiation profile at 2 gigavolt compared with copper K alpha emission. The X-ray radiation are emitted from copper, and the characteristic X-rays are K alpha. On the y-axis is intensity of photon, and on x-axis is photon energy. Two crystals are used to make the exit beam parallel to the entrance beam. Curve crystals focus on the X-rays. So these one crystal and two crystal in double crystal monochromator. These two crystals, why these two crystals are used? Because due to these two crystals, this is exit beam and this is entrance beam. So exit beam is parallel to entrance beam due to reflection from these two crystals. So that is why these two crystals are used, and these two crystals are used in curve form, because in curve form there is more focusing of radiations. The wave of the ejected photoelectron from the K shell can be thought of as spherical waves. So this is the absorbing atom. This atom will absorb the X-ray radiation. X-ray photon will be absorbed by this atom, and the electron will be ejected. K shell electron will be ejected from the attraction of the nucleus, and this ejected electron will have a spherical wave. It will be in the form of spherical wave. Okay, it will be emitting from the nucleus of the absorbing atom. It will be free from the nucleus attraction, and it will form an electron wave. This electron is photoelectron. This electron is also called photoelectron because this can produce a photon. This encounter neighboring atom and is partially scattered by them, producing a phase shift. So this electron wave will interact with the neighboring atoms. So neighboring atom will backscatter this electron wave. So this is backscattered electron wave, a new electron wave which is outgoing electron wave. Between these two electron waves, interference can take place. Backscattered electron wave which is scattered due to neighboring atoms, and outgoing electron wave which is coming from this atom. Interference can take place. If they are in phase, a constructive interference will take place. Here is the example of constructive interference between the backscattered electron and outgoing electron, and here is the destructive interference between the backscattered electron and outgoing electron. So this encounter neighboring atom and is partially scattered by them. Photoelectron is partially scattered by the neighboring atom, producing a phase shift. As phase shift will be produced. Depending on the phase shift experienced by the electron, the reflective waves can then interfere interfere constructively or destructively with the outgoing wave, so producing a net interference pattern at the nucleus of the original atom. So at this original atom, interference will be produced. It may be constructive and it may be destructive interference depending on the phase shift. Absorption by the original atom is now modified and the effect is seen as sinusoidal isolation of the fine structure. So due to this constructive and destructive interference, this type of waves will be formed. Absorption by the original atom is now modified in the form of these peaks, and the effect is seen as sinusoidal oscillation of fine structure. This type of fine structure isolation are obtained due to constructive and destructive interference superimposed on the absorption edge. This is the which is the sharp peak, highest peak. This is the absorption peak. So here the these type of structures or oscillations are formed due to constructive and destructive interference, which are superimposed, which these isolations are also superimposed on the absorption edge, extended out to the several hundred electron volt after the edge. These type of oscillation are also superimposed on the absorption edge, and these are also formed at several hundred electron volt after the edge. The on x-axis is kilo electron volt, so 700 means near the edge these isolations are also formed. At several hundred electron volt distance, these isolations are formed. The extent to which the outgoing wave is reflected by a neighboring atom, and so the intensity of the reflected wave is partly dependent on the scattering factor of that atom. Outgoing wave is reflected by neighboring atom. We have that previously studied that this electron wave is going and neighboring atom will reflect this electron wave, and the extent of this reflection depend on what? Intensity of the reflected wave depend on what? It depend on the scattering factor of that atom, how that atom is able to scatter the electron. And scattering factor depend on the electron cloud. More dense is electron cloud of the neighboring atom, it will scatter more the outgoing electron wave.